Here's a puzzle for you. You take a balloon, the kind a child has at a birthday party. You rub it on your head. Then you hold it up near your hair, and the hair reaches for the balloon like it's trying to climb back up. Every child has seen this. Every adult has stopped paying attention to it. And I'm going to tell you something now that ought to bother you a little. Nobody on this planet, not the chemists, not the physicists, not the engineers, who use this trick every single day to keep the laser printers in your office running, can tell you exactly what just happened on that balloon. We have been arguing about it since the ancient Greeks. A fellow named Thales of Miletus, around 2,600 years ago, picked up a piece of amber, rubbed it with fur, and noticed it pulled little bits of straw toward it. The Greek word for amber is electron. That's where we got the word electricity. We've had a name for this thing longer than we've had most of our cities, and we still cannot agree on what it is. I want to walk you through this carefully, because the more you look at it, the stranger it gets. And by the time we are done, you'll feel something a little peculiar. You'll feel that you have been living your whole life next to a small, everyday miracle, and nobody told you it was a miracle. Let me say what we do know. When you rub two things together, one of them sometimes ends up with extra electric charge of one sign, and the other ends up with charge of the opposite sign. The fancy name for this is contact electrification, or the triboelectric effect, from the Greek word tribo, which means rubbing. It is the reason your sweater crackles when you peel it off in winter. It is the reason a comb pulls little pieces of paper after you run it through your hair. It is the reason lightning forms in clouds. It is the reason photocopiers and laser printers exist at all. And it is almost certainly the reason for a number of very large industrial explosions every year in flour mills, in grain elevators, in factories that handle fine powders. So this isn't some obscure laboratory curiosity. This is one of the most ordinary, most pervasive phenomena in your daily life. And I am telling you that the people who study this for a living fight about how it works, loudly, in journals, with papers titled things like The Unsolved Problem of Contact Electrification. Why? Let me start at the beginning, because I think it helps to see how patient and confused humanity has been about this. Thales sees the amber pulling at the straw and writes it down. Then nothing much happens for about 2,000 years. 2,000 years, where every village had wool and resin and dry weather, and nobody investigated. Aristotle mentions the amber. Pliny mentions the amber. They knew. They just didn't know what to do with it. Then in the year 1600, an English doctor, William Gilbert, published a book on magnetism. And in this book, he made a careful distinction. He said magnets are one thing, an amber effect, the rubbing thing, that's something else. He coined the word electricus to mean behaves like amber. Gilbert was a careful man. He listed many materials that show the amber effect: glass, sulfur, sealing wax, certain stones. So now we have a category. We have a name. We still have no idea what is going on. Around 1660, a German fellow named Otto von Guericke built the first electrostatic generator. It was a ball of sulfur about the size of a melon, mounted on a crank. You spun it and pressed your hand against it as it turned. Sparks flew. Feathers leapt up to it. People made parlor demonstrations out of this. Show up at a dinner party, light a piece of paper on fire with a spark from your fingertip. Very impressive. Still no theory. Still nothing about why. Then along comes Stephen Gray in 1729, who notices that some things let the electricity travel through them, and some things stop it cold. He hangs a boy from silk threads, charges his feet, and watches little brass leaves jump up to his hands. He's discovered the difference between conductors and insulators, although he calls them by different names. The puzzle is starting to get interesting. Some materials carry the strange stuff. Some don't. But still, what is it? A few years later, a French chemist named Charles-François de Cisternay-Dufay does something clever. He notices that there are two kinds of electricity. He calls them vitreous, from glass, and resinous, from amber and rubber. Two pieces of glass that have been rubbed will repel each other. Two pieces of amber rubbed will repel each other. But a piece of glass and a piece of amber will pull together. Two flavors then, not one. Now Benjamin Franklin enters the story. And Franklin makes a big simplification. He says, no, there's only one electricity, but there's an excess and a deficit. Things with too much of it he calls positive. Things with too little he calls negative. This was a guess, by the way. He guessed wrong about which was which, but the convention stuck, and that's why electrons, which are what actually moves in a wire, are negative. Franklin couldn't have known. He was making sense of a thing he'd never seen. So now, at the end of the 1700s, we have a picture. There is some kind of stuff. It comes in positive and negative. Rubbing two things together moves it from one to the other. The thing that gives it up becomes negative. The thing that takes it on becomes positive. Or maybe the other way around. Depends on the materials. Beautiful. Now we just have to figure out which materials give and which materials take. This is where our investigation properly begins. Because here's what people did next. They started making lists. Around 1757, a Swedish fellow named Johann Carl Wilcke wrote down what we now call the triboelectric series. It works like this. You take a long list of materials: air, hands, glass, hair, nylon, wool, fur, silk, paper, cotton, wood, steel, hard rubber, polyester, plastic wrap, polyethylene, vinyl, silicone, Teflon. You arrange them in order. The materials at the top become positive when rubbed. The materials at the bottom become negative when rubbed. And the further apart on the list, the bigger the charge transfer. So if you rub a glass rod with a piece of silk, the glass becomes positive and the silk becomes negative. Why? Because glass is higher on the list. If you rub silk with a piece of Teflon, the silk becomes positive, because now the silk is higher on the list. Silk doesn't have a fixed identity. Glass doesn't have a fixed identity. It depends on what you rub them against. This is what every introductory physics book teaches you. And when I first saw this, I thought, well, that's a beautiful little system. We've got it figured out. We've got a list. We can predict. The mystery is solved. We just have to understand why some materials want to give up charge and others want to take it on. That's a chemistry problem. We'll get there. Except, there's a problem. The list doesn't work. Let me tell you what I mean by that. If you take three materials, A, B, and C, and you arrange them in a triboelectric series, you should get a consistent ordering. A always charges positive against B. B always charges positive against C. So A should always charge positive against C, right? Like sorting marbles by weight. If marble 1 is heavier than marble 2, and marble 2 is heavier than marble 3, then marble 1 is heavier than marble 3. Always. Forever. That's what ordering means. Except materials don't behave like marbles. There are well-documented experiments where A charges positive against B, B charges positive against C, and then C, when rubbed against A, charges positive. The list goes in a circle. You can chase your tail with it. That alone should give you pause. But it gets stranger. Take a single material. Pure polystyrene, say. The same chunk of plastic. Rub two pieces of it against each other. According to any theory where some materials prefer to give and others prefer to take, this should do nothing. They're the same material. Same chemistry. Same atoms. Same everything. There's no asymmetry. There's nothing to drive a charge transfer in any direction. But it doesn't do nothing. It transfers charge. Sometimes a lot. One piece becomes positive. The other becomes negative. Two identical chunks of plastic. And somehow they decide which one of them gets the surplus and which one gets the shortage. Like two identical twins, rubbed together, ending up with different bank accounts. How does a piece of plastic know which side of itself is the giver and which is the receiver? It can't, by anything we understand. The whole thing should be symmetric, by basic physics. And it isn't. This was a clue. People wrote it down. People published it, and for a long time people sort of looked away. Because if you can't explain identical materials charging each other, your theory is in trouble, and nobody wanted to admit how much trouble it was in. Then in the year 2011, a chemist named Bartosz Grzybowski and his team at Northwestern published a paper that I think broke the field open. They were doing something simple. They took a piece of polymer, brought it into contact with another piece of polymer, separated them, and then they did something nobody had bothered to do carefully before. They mapped the charge, not just the total charge. The location of the charge. Where on the surface was it positive? Where was it negative? They used a technique called Kelvin probe force microscopy, which is just a fancy way of dragging a sensitive needle across a surface and recording the local voltage at every spot. What they found was bewildering. The surface wasn't uniformly positive or uniformly negative. It was a mosaic, a chessboard. Patches of positive charge sat right next to patches of negative charge, all on the same surface, on the same material, after the same single rubbing event. The total charge of the surface might be slightly positive or slightly negative, but locally you'd see plus, minus, plus, minus, plus, scattered like spots of paint. And the same was true on the other surface. Mosaic over there too. Plus and minus next to each other. I want you to picture this. You take two pieces of plastic, you touch them together, you pull them apart, and on each surface where they touched, there is now a fine pattern of positive and negative islands. Hundreds of microscopic batteries, alternating sign, packed together like a quilt. Now think about what this is telling you. If contact electrification were a clean process, where one material is the giver and the other is the taker, you would not see this. You would see one surface uniformly negative and the other uniformly positive, like two plates of a capacitor. You'd see a clean transfer. Instead, you see chaos at the small scale and only an average tendency at the large scale. That experiment buried the simple electron jumping picture. It also threw the triboelectric series into a kind of philosophical trouble. The series describes the average. It doesn't describe what's actually happening. The series is what you get when you look at the whole surface and add up all the patches. The patches are what's really there. And nobody knew, when Grzybowski's paper came out, what was making the patches. So what is transferring across that contact? What is the material we're moving? Now you'd think this would be the easy part. You'd think after 2,600 years, we'd at least have nailed down the substance involved. But this is exactly where the modern argument lives. There are, I'll tell you honestly, at least 4 mechanisms that have been proposed, each by serious people, each with experimental support, each with problems. Let me lay them out one by one. The first idea, and the most natural, is that what gets transferred is electrons. Electrons are negative. They're tiny. They're mobile. When two surfaces come into close contact, electrons hop from one to the other, depending on which material binds them more loosely. The material that loses electrons becomes positive. The material that gains them becomes negative. This is the picture you probably have in your head, and it works beautifully for metals. When two metals touch, electrons absolutely do flow between them, and the side with the lower work function loses electrons. The trouble is, the things we usually charge up by rubbing are not metals. They are insulators. Glass, plastic, wool, hair, rubber. In an insulator, the electrons are bound. They don't roam around. The whole point of an insulator is that electrons can't easily move through it. So how are they jumping out of one insulator and into another? The energy required to free an electron from a typical polymer is enormous. The thermal energy at room temperature is nowhere near enough. People have argued for years about this. Some say there are special surface states, little energetic traps that electrons can hop between. Some say the contact pressure does something to lower the barrier. Some say no, electrons are not what's moving here. The case for electrons is strong for some systems, weak for others, and contested everywhere. The second proposal is that what's moving isn't electrons at all. It's ions. Whole atoms with extra or missing electrons, dragging along. This idea was pushed strongly by a chemist named George Whitesides at Harvard, working with his postdoc Logan McCarty around 2008 and onwards. They argued that on most real surfaces, especially in normal humid air, there is a thin layer of water and dissolved ions, hydroxide ions, hydrogen ions, other contaminants. When two surfaces touch, these ions get partitioned unequally. One surface ends up with more positive ions, the other with more negative ions. The bulk material doesn't even need to give up its own charge. The mobile ions on top do all the work. This explains a lot of things. It explains why humidity affects static electricity so dramatically. On a humid day, your sweater barely crackles. On a dry winter day, it crackles like a campfire. If ions on a water layer are doing the work, humidity changes the ion population, and that changes the charge transfer. It also explains why two pieces of the same material can charge each other differently. Two identical pieces of plastic, if they have slightly different surface ion populations from their previous history, will partition those ions unequally when they touch. Beautiful. So is it ions? Probably sometimes, but here's the trouble. People have done the experiment in a vacuum, with bone-dry surfaces, and the contact electrification still happens. It's weaker, but it's there. And in pure water-free systems with very clean materials, you can't have ion transfer. So ions can't be the whole story. They are part of the story, especially in everyday conditions, but not the only mechanism. The third proposal is even stranger. It says that what gets transferred is bits of material itself. Tiny chunks, polymer fragments, molecules torn off one surface and stuck onto the other, carrying their own charge with them. This sounds wild, until you think about what really happens when two surfaces touch. They don't kiss politely on a flat plane. At the molecular scale, they crash, they crush, they grind. There are sharp asperities, little hills and valleys. When you press them together and slide, you're tearing off fragments. Polymer chains break. Small pieces transfer. The atoms in those pieces have charges associated with them, sometimes ionized at the moment of breaking. So you could get charge transfer simply by transferring stuff. Grzybowski's group, after the Mosaic experiment, did a follow-up where they actually detected polymer fragments on surfaces that had been brought into contact. There was material transfer, real physical material moving between insulators just from touching, tiny but measurable. So now we have three pictures: electrons jumping, ions migrating, material chunks tearing free. And every one of them seems to happen, depending on what materials you use, what conditions you're in, what scale you look at. The fourth proposal is even subtler, and it's relatively new. It's called bond cleavage. The idea here is that when surfaces come into contact and then separate, you stretch and break chemical bonds. Now, when you break a bond, there are two ways it can come apart. One way, both electrons stay together on one side, and the bond becomes ionic. The other way, the electrons split, and you create two free radicals, each with one unpaired electron. If the breaking is asymmetric, charge ends up on one side of the broken bond. The surface that holds the bond fragment with the extra electron becomes negative. The other becomes positive. Multiply this over millions of bonds breaking at the contact zone, and you get a charged surface. There are research groups, especially Lawrence Marks's team at Northwestern, who have argued that bond cleavage and the radicals it creates are the most underrated mechanism in the whole field. So now four mechanisms: electrons, ions, material transfer, bond cleavage. None of them entirely correct. None of them entirely wrong. Now I want to add one more wrinkle, because this story isn't just about chemistry. There's a piece of physics that has come back into the discussion in the past 10 years, and it's called the flexoelectric effect. Flexoelectricity is what happens when you bend a material, and the bending itself creates an electrical polarization. Push some materials, and they get polarized at the squeezed end. Bend them, and you get a separation of positive and negative charge across the bend. This is different from piezoelectricity, which only happens in special crystals. Flexoelectricity happens in basically any insulator, if the gradient of the bending is sharp enough. Now, when two surfaces come into contact, even smooth-looking surfaces, at the microscopic level there is enormous local bending. Tiny asperities press into each other, and the curvature at the point of contact is sharp. So there is, automatically, a little flexoelectric polarization happening at every point of contact. Daniel Lax, at Case Western Reserve, has done some lovely experiments on this. He took granular materials, all of the same chemical composition, just different sizes of grains, and bounced them around together. The big grains charged positive. The small grains charged negative. Every time, with chemically identical particles. Why? Because the small grains have more curvature, more bending per contact, more flexoelectric effect. The asymmetry isn't in the chemistry, it's in the geometry. That's a lovely result. It explains how you can get static electricity in dust storms, where all the particles are the same kind of dust, just different sizes. The fines charge negative, the coarse charge positive. The atmosphere ends up with a separation that isn't chemical, isn't thermal, isn't anything we used to call by a name. It's a geometric flexoelectric effect, and it happens because particles of different sizes touch each other unequally. So now you have 5 candidates for what's actually happening when you rub a balloon on your hair. Electrons hopping, ions migrating across a water film, polymer fragments tearing off, bonds breaking with asymmetric electron distribution, flexoelectric polarization at points of contact. What do you think the right answer is? I'll tell you what I think the right answer is, because we have arrived at the place I've been building toward. The right answer, the one that is gaining ground in the journals right now, is that there is no single mechanism. There is no one thing called static electricity. The phenomenon we point to and name contact electrification is a category, not a process. It's a label we slapped on a bunch of different phenomena that all happen to produce a similar end result, namely a piece of material with an excess of charge. In any given rubbing event, on any given pair of materials, in any given humidity and temperature, several of these mechanisms are happening at the same time. Electrons may be hopping in some places. Ions may be migrating in others. Bonds may be cleaving here and there. Material fragments may be transferring. And under it all, the geometry of contact may be polarizing the local material flexoelectrically. The total charge you measure at the end is the sum of all of these processes, each pulling charge in its own direction, sometimes adding, sometimes canceling, sometimes producing the Mosaic patches that Grzybowski photographed. This is why the triboelectric series sort of works, but not really. It's an average over many mechanisms. This is why 2 identical pieces of plastic can charge each other. The mechanisms don't care about chemical identity, they care about geometry, history, surface contamination, contact pressure, separation speed, and the roll of the dice at the molecular scale. This is why you can get cyclic violations in the series. The dominant mechanism between A and B might be different from the dominant mechanism between B and C. You're not measuring the same physics at every step. We named it before we understood it. We thought we were naming one thing. We were naming a confusion, and the confusion has stayed with us for 2.5 millennia, hidden inside a very simple-looking word. Let me tell you why this matters, beyond intellectual itch. It matters first because of money, a lot of money. The photocopier industry, the laser printer industry, every one of those machines works by depositing charged toner onto a charged drum, transferring it to charged paper, and fusing it. Every step uses contact electrification. Engineers at Xerox in the 1970s and 80s built laser printers without ever fully understanding the physics of the charge transfer. They tuned it empirically. They tried materials. They settled on combinations that worked. Whole multi-billion-dollar industries sit on top of this not quite understood phenomenon. It matters because of explosions. In any factory that handles dry powder, flour, sugar, coal dust, certain pharmaceuticals, the powder rubs against itself and against the equipment as it flows. It builds up charge. Eventually a spark jumps, and the dust ignites, and the factory blows up. Every year people die from this. Engineers know roughly what to do: ground everything, humidify the air, choose materials carefully. But we cannot predict from first principles which combinations are dangerous. We test, we measure, we hope. It matters in semiconductor manufacturing, where a tiny static discharge can fry a microchip the second it leaves the assembly line. Whole industries of static-controlled bags and grounded wristbands and ionized air blowers exist because we can't fully prevent contact electrification. We just damp it down. It matters in lightning. The biggest unsolved puzzle in lightning research is exactly how the inside of a thunderstorm cloud separates positive and negative charge. There's a leading theory that ice crystals and softer ice pellets called gropel collide and exchange charge, and the lighter crystals get carried up while the heavier gropel falls down, separating the cloud vertically. This is a contact electrification process, exactly the same kind we've been talking about, and we don't fully know which mechanism dominates inside a cloud. Lightning, the most spectacular electrical phenomenon you can see from your backyard, the thing that probably gave early humans the idea that the sky was angry at them, is powered by physics we cannot fully write down on a page. There is also a recent twist that comes the other way around. If contact electrification produces real charge, and we now half understand it, can we harness it? Can we make small generators that produce electricity from movement just by rubbing materials together? The answer turns out to be yes. And a Chinese-American physicist named Zhonglin Wang, working at Georgia Tech, started a whole field around 2012 called triboelectric nanogenerators. These are tiny devices that flex, contact, separate, and produce useful current. They can power small sensors. They can capture energy from your footsteps, from raindrops, from ocean waves. The same physics that makes your sweater crackle, scaled and arranged carefully, can run a wristwatch. So we use it. We profit from it. We die from it. We write papers about it. And we still argue. The argument is fascinating to me because it tells you something about how science actually works, as opposed to how we tell people it works. The story we tell in textbooks is, a phenomenon is observed, a theory is proposed, the theory is tested. If it works, it becomes part of the accepted body of knowledge. We move on. Science marches forward in a tidy way. That isn't what happens with contact electrification. With contact electrification, the phenomenon was observed 2,600 years ago. Many theories have been proposed. Each works for some cases. None works for all. And the field has not moved on, because there isn't anywhere clean to move on to. Every textbook still teaches the triboelectric series as if it were a settled rule, even though every researcher in the field knows it's a rough average over a chaos. Every freshman physics class teaches that rubbing transfers electrons, even though that's almost certainly only one of several things happening, and not always the dominant one. We carry around incomplete pictures. We use them. They serve us. And underneath them, the real physics is messier and more interesting than what we tell ourselves. I think that's true of a lot of physics, by the way. The neat stuff in textbooks is the part where we found a clean answer. The messy stuff, the unfinished stuff, the stuff that's been argued about for centuries, is mostly hidden from view. You have to dig for it. You have to ask questions like, but how does a balloon really pull at hair? And you discover that nobody knows. And you realize that the world is full of these little holes. And the holes are where the future of science actually lives. I want to leave you with one thought. I want you to think about this the next time you take off a sweater in the dark, in winter, and you see those tiny blue sparks on your shoulders. Each one of those sparks is an unsolved problem. Each one is a little fight. Each one is a thing the ancient Greeks saw and named, and we still haven't fully explained. You are watching, with your own eyes, a piece of physics that has resisted humanity for longer than humanity has had writing in some places. The miracles aren't all in the heavens. They're in your laundry. And the whole business reminds me, in the end, that the words we use can fool us. We have a word, electricity, and because we have a word, we feel like we have a thing. We say static electricity and our brain hears a phenomenon, well defined like gravity or light. But it isn't a phenomenon. It's a confusion of phenomena. It's at least 4 or 5 different physical processes, all crammed into the same name, all happening at once, contributing to a single number we measure on a meter. We labeled the bag without labeling the contents. A lot of science, when you really look at it, is unpacking the bags. Finding out that what you thought was one thing is many things. Light is a wave, but also a particle. Heat is energy, but also disorder. Time is duration, but also coordinate. Gravity is a force, but also a curving of space. And static electricity, this most ordinary, most childish, most unremarkable phenomenon, is at least 4 things wearing a single name. You walked into this lecture, I hope, thinking you knew what static electricity was. A balloon that grabs your hair, a sweater that crackles, a doorknob that bites you when you reach for it. Settled physics. Done. Now you know that the people who do this for a living have argued about it for centuries, and they're still arguing, and the argument is not about minor details, it's about which mechanism dominates, and the answer keeps depending on the question. I'd like you to tell me one thing, if you'll humor me. Think of another phenomenon you assume is settled. Something so ordinary you've never questioned it. The way water beads on a leaf, the way bread rises, the way ice forms patterns on a winter window. Pick one and ask yourself, do I actually know why? Or did somebody just give me a name for it? Tell me which one you picked. I'd love to know what you find when you start to unpack the bag.